Principles of Operating Systems, Chapter 7, Organization of Information. Computers are digital devices. Information in computers is represented in binary format using zeros and ones, using bits. Since the amount of information you can represent with a single bit is limited, to say the least, computing systems typically use combinations of bits. Some of the combinations that are used are known as bytes, words, double words, blocks, pages, files, directories. Each of these is used to represent or help or manipulate certain kinds of information, and generally several different kinds of information. A byte is a unit of digital information, usually of 8 bits of information. Historically, the byte started off being just the number of bits used to encode a single character in a given computer. Now, many of the computer architectures, that would tend to mean the smallest addressable unit of memory. Historically, the size of the byte was hardware dependent, and there weren't any standards mandating the size of what was called a byte. They went anywhere from 1 up to 48 bits in some computers. Now, the earlier character encoding schemes often used 6 bits, and quite a few machines used 6-bit and 9-bit bytes up into the 1960s. These 6-bit, 9-bit machines typically had memory words of size 12, 24, 36, 48, or even 60 bits. 2 bytes, 4 bytes, 6 bytes, 8 bytes, or 10 6-bit bytes. The modern standard of 8 bits for a byte, it's a convenient size. It's a power of 2. It can represent integer values from 0 up to 255, which is a standard size, a convenient number of convenient range of numbers. Many kinds of applications use information that can be represented conveniently in 8 or fewer bits. And processor designers have optimized their processors for this common size. The popularity of commercial computing architectures using 8-bit bytes has added to the popularity of the 8-bit size. The 8-bit microprocessors in the 1970s made the 8-bit size even more pervasive. Some microprocessors, starting with the Intel 8008, which was the predecessor of the 8080 and 8086, could deal with 4-bit bytes, 4-bit units, which would combine to make a byte. the 4-bit quantity, sometimes referred to as a nibble. And it's convenient also because it stores numbers that can be represented can be represented conveniently with a single hexadecimal digit. Many programming languages also have a data type named byte, conveniently, normally 8 bits. Now, data transmission has a slightly different take on it. The byte is a contiguous sequence of bits in a serial data stream with the smallest possible distinguishable unit. A transmission unit would include start bits, stop bits, parity bits, and can vary anywhere from 7 to 12 bits to contain a 7-bit ASCII code. Each byte in memory will have an address identifying its location, and each combination of bytes, words in their larger sections, would have addresses too, but those would be derived from the bytes that make up the larger unit. In computing, the term word refers to the natural unit of data for the given processor, a fixed size piece of data that's handled as a unit by the instruction set and/or hardware for the processor. The word size, word width, number of bits in a word is an important characteristic for any specific processor design or architecture. Typically, modern architectures are using 32-bit words and 64-bit words, which can consist of 4 8-bit bytes or 8 8-bit bytes. The size of a word has a lot of effect on the computer structure and its operation. The majority of the registers in a processor are usually the size of a word, and the largest piece of data that will be transferred to or from the working memory in a single operation is a word in many architectures, not all of them. In particular, the 8088 would transfer 8 bits at a time, but the word size, the register size, was 16 bits. The largest possible address size would generally be the number that could be stored in a word. Modern processors generally have word sizes of 8, 16, 24, 32, and/or 64 bits. The general purpose computers usually have word sizes of 32 or 64 bits. Special purpose processors use other sizes, and historically, words have been many different sizes: 9, 12, 18, 24, 26, 36, 39, 40, 48, and 60. Some of the earliest computers, and there are a few modern ones as well, use binary coded decimal instead of binary. They typically have word sizes of 10 or 12 digits. Some early decimal computers didn't have the concept of a word built in at all. Now, the size of a word can sometimes be different from what you would expect. Usually, in order to support backward compatibility, backward compatibility with earlier computers. If multiple compatible variations of a family of processors share a common architecture and a common instruction set, but different word sizes, documentation and software could be complicated to accommodate the difference. A cache is a section of memory that uses faster memory. It's used to store copies of data that are being referenced so that they can be processed more rapidly. Most CPUs have different caches, have a cache for instructions and a cache for data. The data cache usually gets organized into several layers, L1, L2, L3, and so on. Data gets transferred between memory and cache, regular memory and cache, in blocks or lines of fixed size. When the cache line is copied from memory into cache, a cache entry is created. The cache entry will include the data and also an identification, a tag identifying what in main memory this line copies or represents. So you're going to have a tag identifying what it is this data is a copy of, the data, and then bits to identify status. When a processor has to reference or use a location in RAM, main memory, the first thing it does is checks for a corresponding entry in cache. It checks for the contents of whether that entry is in, has a representation, that data has a representation in cache, tries to find the location that copies the data. If it finds that the memory location is represented in cache, we have a cache hit. If there is no entry in cache copying that data in main memory, then it's a cache miss. In the event of a cache hit, the processor goes ahead and uses the cache memory to process the command that it is executing. If it's a cache miss, the system allocates a new entry in cache, copies the data from the main memory into the new entry, and then proceeds to execute the command using the cache entry for fast processing. The original Pentium 4 had an L1 data cache of 8 kilobytes divided into blocks of 64 bytes each. It also had an 8-way associative L2 cache of size 256K divided into blocks of 128 bytes each. As this illustrates then, you can have different cache blocks of different sizes in different systems, and even cache blocks of different sizes on the same system. With the development of the virtual memory systems and disk cache systems, it started being desirable to divide the system RAM into sections of uniform sizes that would be convenient for reading to and reading from hard disk. These subdivisions they called pages. A sector is a subdivision of a track on a hard disk or an optical disk. Each sector stores a fixed amount of data, traditionally 512 bytes for a hard disk, 2K bytes for CDs, DVDs. Newer hard disks use advanced format 4K bytes in a sector. The sector is what gets written to, read from, the basic storage unit on a hard drive. Most disk partitioning systems are designed to have files that occupy 1, 2, 3, an integer number of sectors, regardless of the file size. If it doesn't fill out a whole sector, the remainder of the sector gets filled with zeros. The process of reading from or writing to a disk involves two steps. First, it has to move the read-write head to the correct track. Then it has to wait until the correct sector rotates, as the disk spins, rotates into the position where the read-write head is. Then it does the reading and writing. Moving the head to the track is the slow part. Takes more time. That's the latency. The read-write, the rotational delay, the wait until the correct sector comes to the read-write head, is faster because the disk is spinning very fast. If we're reading to, writing from, writing to, reading from more than one sector, then it's more efficient if we don't have to move the read-write head again until the reading and writing is done. So it's more efficient to have data that's referenced together stored on the same track. The idea of the virtual memory system is to store and load sections of data that's going to be referenced together, so it makes sense to store and load data together as pages onto the same track. So the pages should end up being multiples of sector size, so that the hard disk uses. Memory segmentation is the division of the primary memory into sections called segments. Segments are very much like pages, except that pages have a uniform size, segments do not necessarily have all the same size. If a computer uses segmentation, a reference to a memory location would include a value identifying the segment and an offset within the segment, very much like paging. Segments usually correspond to divisions of a program, functions, subroutines, entire libraries, or data tables, and is generally programmed, controlled by the programmer, where paging is built in with the operating system. Different segments can be created for different program modules, for different classes of memory usage, code or data, can also be used by more than one program. Computer file is a resource or construct for recording or storing data on an external storage device, principally a hard disk. There are lots of different kinds of computer files designed to serve different kinds of purposes. They can store a picture, a text message, a video, computer program, many other kinds of data. Some kinds of files incorporate various kinds of information, multimedia files. By using computer programs, a person can open a computer file, read the contents of the computer file, change or modify the contents of the file, close the computer file. And they can be reopened, modified, recopied any number of times. Typically, files are organized in a file system. It keeps track of where the files are located in secondary storage and allows the users to access them. Most modern operating system, a file, is organized and stored as an array of bytes. The format for the file is basically what it will need to represent its content. The file is just a container for some collection of data. Some platforms require that the file extension dictate what kind of data should be stored in it or how the data should be interpreted. A file with an extension txt, the bytes in the file should represent ASCII characters, ASCII codes for characters, or UTF-8 codes for characters. But in an image file or a video file or an audio file, the content of or the interpretation of a byte or collection of bytes would be very, very different. Most file types also allocate a few bytes at the beginning for metadata. allowing the file to carry some kind of basic information about itself. Information in a computer file can consist of packets of information, individually different, but sharing a number of common traits. For example, a payroll file divided into records, each referring to, describing information about an individual employee. But all of these records have a number of common traits related to payroll for that individual. A text file can be made up of a number of lines of text corresponding to how the line would be printed on paper. Or, alternatively, a file might just be an arbitrary binary image, the content of a section of RAM in the computer, binary image. Or it might be an executable, a program, executable code, executable file, binary, that causes the computer to do something when loaded as a program and initiated, as opposed to a data file that has to be interpreted by some other program to be meaningful. The basic things that a program can do with a file are create a new one, change the attributes and access permissions, open the file, making it available to access, read data from the file, write data to the file, terminate the association between the program and the file, to close the file. When smaller and less expensive hard disks started showing up on the market, people recognized that if you used several small hard disks instead of just one hard disk, you end up with a system with a large capacity. Using small hard disks instead of a single large one, you get several advantages. It's usually possible to buy a lot of storage capacity as a combination of smaller, cheaper drives for less money than a single high-capacity drive. The smaller drives are getting manufactured in larger quantities, and so the price has a result of economies of scale. And they are more widely marketed, so they're easier to get a hold of. Reliability as well. If you have several drives and you duplicate the data on more than one drive, then if one drive fails, you still have all of the data available. Finally, access speed. If you have your data distributed over several drives, you can be accessing different parts of the file simultaneously. And so you get faster access times than you would with one drive reading with a single source of input. In a redundant array of inexpensive disks, a RAID system, data can be distributed across the drives in several different ways. The different techniques are referred to as RAID levels, and they vary. They give varying levels of redundancy and varying performances. The different schemes, layouts, are named by levels: RAID 0, RAID 1, RAID 2, 3, 4, and so on. Each scheme, each RAID level, gives a different combination of reliability, availability, performance, and capacity. RAID levels greater than RAID 0 provide protection against sector read errors as well as against failures of entire drives. With RAID 0, there is no redundancy. So there's no improved reliability using multiple drives, but it does give support higher access speeds. With RAID 0, a large file gets divided into several subdivisions called stripes. Different stripes be loaded into different drives. Stripe 1 on drive A on one drive, stripe 2 on another, stripe 3 on another, stripe 4 on another. When you're uploading or downloading files, multiple stripes can be uploaded or downloaded concurrently, simultaneously, which means you can upload 2 or 3 times as fast as you would with one drive. A RAID 0 array with n drives would be reading or writing n drives simultaneously, so you could get up to n times the data transfer rate that you would with one drive. Again, there is no redundancy. Each data point, number, entity gets stored in one place on one drive. As a result, your RAID 0 is going to be used in applications that require fast access, high performance, and can tolerate some level of error, some lower reliability. Computer gaming would be one such application. RAID 1, mirroring. RAID 1 consists of having copies or mirrors of the disks. In this illustration, we have 2 disks, but the system RAID 1 will support more than 2 disks. It can substitute RAID systems in place of the disks. RAID 1 does not use parity, does not use striping. It's primarily useful when read performance is important and reliability is important, but write performance or storage capacity has lower priority. A RAID 1 system will work as long as at least one of the member drives is working. Any read request can be handled by any drive in the array. So depending on the nature of the I/O load, read performance can be as good as the sum of each of the members' performance, because different portions of a file can be read from different disks simultaneously. Write performance, on the other hand, is only as fast as a single disk, since the write performance has to go to both disks, although it can be done to both simultaneously. RAID 1 systems, of course, require twice as many disks as RAID 0 systems for the same storage capacity. RAID 2, very rarely used, stripes data, but at the bit level, bit 1, bit 2, bit 3, bit 4, bit 5. And it uses a Hamming code for error detection. Requires that the disks be synchronized to spin at the same speed, spin with the same angular orientation together, and cannot service multiple requests simultaneously. Has to deal with all of the disks on one transfer. Extremely high data transfer rates are possible using RAID 2. However, all modern hard disks have built-in error correction. So adding the complexity of Hamming code doesn't really offer much advantage over the simpler parity. So RAID 2 has only rarely been implemented, and it's the only original RAID system that's no longer in use. RAID 3, byte level striping with a dedicated parity disk. RAID 3 generally can't service multiple requests simultaneously, rather similar to RAID 2, except we're doing byte level striping instead of bit level striping. Okay. Virtually any I/O operation is going to require activity on every disk. And as with RAID 2, it generally requires synchronization of the disks. It's suitable for applications that demand highest transfer rates in long sequential reads and writes, video editing. Applications with small reads and writes from random disk locations get poor performance from RAID 3. There are, in fact, no significant advantages over other RAID levels, and so it is obsolete. Both RAID 3 and RAID 4 were quickly replaced by RAID 5. RAID 4 is again similar to RAID 2 and RAID 3. We have block level striping instead of bit or byte level striping. We still have a dedicated parity disk. RAID 4 gives good performance for reads, but poor performance for writes because it has to write all parity data to a single disk. So it's always limited by access to the parity disk. Simultaneous read requests for block B1 would have to wait until the request for block A1 is done. RAID 5, which displaced 2, 3, and 4, uses block level striping with parity for error detection, but the parity is distributed over the various disks. Unlike RAID 4, it distributes the parity over the drives. It requires all drives but one be present to operate. Failure of a single drive can be tolerated. It can calculate the necessary values from the distributed parity. No data would be lost, although, of course, loss of a drive will slow the operation significantly. RAID 5 requires a minimum of 3 disks. Distributed parity evens out the stress of dedicated parity disk, and so the efficiency of access is considerably better. Write performance is increased since all of the RAID members participate in a write request. It won't be as efficient as RAID 0 because we're still calculating and writing parity error checking information, but it isn't the kind of bottleneck that RAID 2, 3, and 4 would provide. Since parity calculation has to be performed, small changes in the array will result in write amplification, unnecessarily large amounts of writing to disk. In the worst case, a single logical sector has to be written. The original sector and parity sector need to be read. Original data removed from the parity, new data calculated, and both the new data sector and the new parity sector would then be written. RAID 6 extends RAID 5, adding another parity block. Can use block level striping with 2 parallel parity blocks, both distributed across the member disks. RAID 6 does not have the kind of specific definition and implementation of the other RAIDs. It's simply defined in terms of performance. Essentially, it's a RAID system that will support 2 concurrent disk failures. It has been implemented several different ways, different kinds of error checking, parity and Reed-Solomon, orthogonal dual parity checks, diagonal parity, all have been used to implement RAID level 6. Generally, RAID 6 does not have a performance penalty for read operations, but it does have a performance penalty on write operations because the overhead is associated with parity calculations. It also involves writing to two different error parity disks. Performance varies greatly depending on how it's implemented. In hardware, in software, in firmware, depending on how the error checking is implemented. RAID 6 can read up to the same speed as RAID 5 with the same number of disks.